Hello everybody, this is going to be part 2 of our notes on 4.4 and 6.1. So the last video we ended just before we started talking about triangle area. So we know the area of a triangle equals 1/2 base times height, but as you can see here, what if the height is not given? Well, one option, we can make one. And in this case, it's pretty easy. We can drop an altitude. An altitude is a line that connects a vertex to an opposite side that forms a 90-degree angle. Well, that will allow me to use right triangle trig. Let's include that. You can make one using right triangle trig. So in this case, I am trying to find my height h, and I have an angle and a hypotenuse. So I'm going to say that the sine of 49 degrees equals h over 8. So the height of this triangle will be 8 times the sine of 49 degrees. In this case, our height will be 6.04 inches. Now that I have my height, I can plug in. It's important to pay attention to what other side lengths we have. I created kind of an obvious altitude here, but the important part was that I had the side that I was connecting with a right angle with that altitude. So in that case, this 21 becomes my B value, my base, and my H value is 6.04. My area is going to be 1/2 of 21 times 6.04. Pretty straightforward area here. The area will be 63.40 square inches. So one thing we can do, if I have certain pieces of our triangle, I can drop an altitude and find the height using right triangle trig. The other thing I can do, let's try one more example here. Trying to do the same way. Let's find the area of a triangle where I have A and C and angle B. Let's start by drawing a diagram. I'm going to start with my 120-degree angle. It's going to look something like this. We'll label that angle B. And then we'll connect our other edges here. Our shorter side is down here, so we'll make A. Let's just clean up the edges there. We'll make a small side A at the bottom of 32, and that would make this side C 50. So this one looks a little tricky because while we have the base of 32, we don't have the height, and dropping an altitude seems a little tricky here. Well, in this case, it seems tricky because the altitude is going to exist outside the triangle. Right, so if I were to drop this altitude, I now have a right triangle outside the original triangle. But I can still use that to find my height. I know that this distance here is 60, that angle rather, and what I have here is a 30, 60, 90 triangle. I can use trig or I can use special right triangles to figure out the height of this triangle. In this case, I have the hypotenuse, which is the largest side in a 30, 60, 90. I know that the hypotenuse is twice as big as the smallest side of a 30, 60, 90, and the longest side is going to be 25√3. So this value here that we've just found is our height. So again, we can use area equals 1/2 base times height. In this case, my base was 32, and my height is 25√3. I can plug that into my calculator, and we find our area to be 692.82 units squared. So again, if we don't have the height of a triangle, we can always create one using right triangle trig. When we drop an altitude, it may be like our first example where it's kind of easy to go straight across our triangle. It's also possible that our height exists outside the triangle. That'll happen when we have a base angle that is obtuse, as we have here. So that's one way to deal with area. There's another, and it's called Heron's formula. Heron's formula is a way where if I know all three sides of a triangle, I can plug into this formula and find the area. So there's a couple pieces here that may need a little bit further explanation. There's this quantity S. It shows up quite a few times. This S value is the sum of all three sides divided by 2. So that S value is part of this formula. So the easiest scenario is something like we have on this first example, where they just give us side lengths. It may be more laborious to draw this out and try to sketch and try to drop an altitude. We don't have any angles, so things might get a little tricky. I may need the law of cosines to find an angle. Instead, what we can do here is use Heron's formula. So the first thing I want to do is find S. That's going to be 31 plus 52 plus 28, all divided by 2. In this case, that is 55.5. My recommendation is to use the store function on your calculator. We can actually store this S value so that when I'm typing things in, I don't have to repeatedly type in the same number over and over. Well, what we are actually typing in our area, and we're going to write this all the way out just so we can see where everything's coming from. Our S value of 55.5. That gets multiplied times, I'm going to go in descending order from the largest side to the smallest side just to have some pattern here. I'm multiplying that times 55.5 minus 52 times 55.5 minus 31 and times 55.5 minus 28. We can see here that the square root becomes pretty long. So, but if I have all three sides, this is enough. I can plug that into my calculator and find that the area of this triangle with the given side lengths is 361.76 centimeters squared. The last problem here is a bit of a challenge. I think that you should try it on your own, right? So I'll give you some tips here if you want to get started. My recommendation is that we start this quadrilateral. We start by cutting it along a diagonal. What that does is it ends up creating two separate triangles that we could attempt to solve. We don't know the diagonal length. We may need to find that. But based on this as a first step, we should be able to do what we need to do. I'm going to write everything out as a step-by-step here so you know what I did and why. So if you want to try this before seeing it, I would pause now. All right, team, let's see how we did with this problem. So I'm zoomed all the way out so you can see all the different steps I've done here. This is quite a laborious problem. So the first thing I did before we left is that I cut this this quadrilateral into two triangles. I did this because I don't really have a quadrilateral, a non-regular quadrilateral area formula, but I can work with triangles. So I split my quadrilateral into two triangles. I chose to create this diagonal, knowing that eventually I'd have to cut an angle into smaller parts, and I thought that 100 was just going to be easier to work with. We'll get to that in a minute. So once I split these into two triangles, I started working in that top left triangle because I had the most information to work from. So I used the law of cosines to find the length of our diagonal, which I have labeled as C. So you can see this work here in black. That's my law of cosines, and I just plugged this information directly into my calculator. I found the length of my diagonal. That gives me another piece. It really gives me a third side of this first triangle, right? I had the two on the outside, 15 and 12. Now I have the diagonal. And I know from Heron's formula, if I have all three sides of a triangle, I can find their area. So that's what I did here in blue. I started by finding S was the sum of all three sides in that first triangle. I'm using subscripts here just to keep things organized. So this I'm referring to triangle 1 of the two that I created. So my S1 here was 22.69. And with that 22.69, that's getting plugged into my formula. Again, just to avoid some repetition here, I'm just using S1 as a placeholder. I would use the store feature in my calculator just to save myself a little bit of a headache. When it's all said and done, that first triangle has an area of 89.76 units. We still have quite a ways to go. So we have found this area here. Our work in the left-hand triangle is basically done, but now I need to figure out more from the right-hand triangle. My next step was I need to figure out how that angle of 100 degrees is being broken up. I labeled those angles X and Y, no real reason, just for organization. So I use the law of sines to figure out angles X and Y. That work is here. I started by trying to find X. So I knew that the side across from it was 15 units long. And then I used the sine of 85 degrees and the side across from it. I found that that angle was 54.4. I also know that 54.4 can be subtracted from 100 to find angle Y, which is really what I was looking for. Because I didn't previously have an angle in that second triangle, this opens up our law of cosines. So in pink here, you can see the law of cosines. I solved for Y next. Law of cosines gets a little lengthy, but I found that Y was 13.44. Now that I had Y and C, I really have everything I need. I have all three sides of triangle 2. So at that point, I'm able to find the area, again, using Heron's formula. Using Heron's formula, I find that the second area is 65.73. And my last step is just going to be adding those two triangles together, 89.76 and 65.73, and we get our final area. So I'm just going to zoom back out here and so you can see the work that we've done. All right, there's quite a bit of different pieces here. A lot of the times we have to do what we can. Right? We don't really work with quadrilaterals, so let's break it into triangles. I need to find that diagonal that I've created so that now I have three sides, and then I can use that information to build off of in my second triangle. Nice work today. This will end our notes on 4.4 and 6.1. Thank you very much.